Okay, last video. Let's take an example. There's shown Coulomb's law. Here's shown the hydrogen 1 atom. You may have learned from chemistry. In its nucleus, it has a single proton, and it has a single electron that is zipping around in the first energy shell. And we want to know the force between them. Okay, the electron is a distance of 0.53 times 10 to the minus 10th meters away. So that would be shown here. That is that distance. And now we know the charge on an electron and a proton are the same. And finally, we can define Coulomb's constant. K is 9 times 10 to the 9th with some crazy units that I never remember. And those crazy units are Newton meters squared divided by Coulomb squared. Again, you'll always be given this. So this is simply a matter of putting these charges in. The force would equal Coulomb's constant. And we'll get rid of 9 times 10 to the 9th Newton meters squared divided by Coulomb squared. We'll do all these units, but realize they really don't matter. At the end of the day, you're going to get a force in newtons. And then we do, of course, the charge in absolute value of the electron, which is 1.6 times 10 to the minus 19th coulombs, times the charge on the proton, which is the exact same charge, 1.6 times 10 to the minus 19th coulombs, okay? This would be the electron charge here, this would be the proton, divided by the square of the distance, which we have shown there. So then we would simply write 0.53 times 10 to the minus 10th meters squared. Okay, so you put this all in your calculator. I suggest doing the numerator as one step and then dividing by the denominator squared as the second step. And you'll get a force, like any other force. In this case, it's a small number, 8.2 times 10 to the minus 8 newtons. Something to note about this, and I'll let you focus in on this here, pause the video. This seems to be a really small force. Realize this is in a really small area, minus 10th meters. This is actually a ridiculously large force. When you start messing with these forces, as you can see here, you get nuclear reactions such as nuclear fusion, which is powered by hydrogen as well, shown here, which you don't need to know. I'm only showing you this, that this powers the sun. So you can think this force here, holding protons and electrons together, is quite actually a large force with a lot of energy. Going a bit further from nuclear fusion, sun being a good thing, we can show you another picture here that if you disrupt the forces, nuclear reactions occur, if you're disrupting forces in the nucleus, that actually leads to a thermonuclear weapon, shown here as a hydrogen bomb, which is a terrifying weapon of mass destruction. So this small force, actually an enormous force on the scale of the nucleus. Okay, once again, nuclear bomb, nuclear reactions when you disrupt these type of forces, and nuclear fusion reactions which power the sun. Only show you those as examples of applied physics. And I'll focus on this and you can pause and that. So these proton and electron exert this force on each other. It's equal and opposite. They point inward because they are both attracted to each other. So each of these exerts this force on each other, which is an attractive force.